Okay. Well, good morning to our Japanese attendees and participants. Good afternoon to the Americans. Good afternoon, good morning to everybody all over the world. Welcome to the I²CNER webinar series. I am Petros Sofronis, the director of the Institute, and I'd like to let you know that this is another webinar that we have in our Institute. And as you know, webinars are important venues that we use in order to discuss recent developments or exciting future developments, and we invite distinguished speakers from all aspects of the society, academia, industry, and organizations to discuss with us, as I said, the recent developments and exciting future directions in science. And today's speaker will be introduced by Professor Ken Christensen, who is the Dean of Engineering at the Illinois Institute of Technology. So Ken, the floor is yours.
Thanks, Petros. It's my pleasure to be your host for today. Today's speaker is Professor Yaofa Lee. Dr. Lee is an assistant professor in the Department of Mechanical and Industrial Engineering at Montana State University. He received his bachelor's degree from the University of Science and Technology of China and a PhD from Georgia Tech, which he finished in 2015. I was then lucky enough to recruit him to the University of Notre Dame, where I was before this, as a postdoc. And part of his work was actually funded by the I²CNER Institute. So Dr. Lee's research focuses on development of experimental methods for thermal fluid problems, primarily at the microscopic scales, with applications in thermal sciences, multiphase flow, and mineral dissolution in porous media. I'm really proud of Yaofa because he was recently awarded a National Science Foundation Career Award, which is a very prestigious grant for new young faculty members in the United States. And he's also a recipient of a Doctoral New Investigator Award from the American Chemical Society Petroleum Research Fund. So congratulations for that, Yaofa. Today, his talk is titled Quantifying Pore-scale Interactions of Multiphase Flow in Porous Media using Microfluidics and Advanced Flow Diagnostics. Before we start, I'd like to take a moment to remind you that your questions will be addressed after the presentation. So please use the raise hand button or type your question or comment in the Q&A box. When you're called on, please unmute yourself. This webinar is also being recorded and will be made available on the I²CNER website. So now everyone, please welcome Professor Lee. Yaofa, go ahead.
Thank you. Let me share my screen real quick so they can all see me. Okay, you see me now? Okay. All right, good morning, good afternoon, and good evening, everyone. Thank you, Professor Christensen, for the introduction. That was very generous. And I really want to thank you for the invitation and opportunity for me to present at I²CNER webinar. It's a really great honor for me. And of course, I would like to thank my former postdoc advisor, Professor Christensen, for generously passing along this opportunity to me. In fact, a majority of part of this work that I'm going to talk about today was performed at the University of Notre Dame, where I was a postdoc working with Dr. Christensen. And this work was also partially supported by I²CNER, as mentioned by Dr. Christensen. And this presentation is kind of a summary of the 5 or 6 papers that we have published in the past several years, and which also have contributions from Dr. Al Valoki from University of Illinois, and Dr. Diogo Boster from University of Notre Dame, and also my colleagues at University of Notre Dame, Gianluca Blois, Dr. Gianluca Blois, and Dr. Fazan Kazmi-Fair, who is an assistant professor at San Jose State University now. And some of the work was also done by my own students at MSU, Razan Mola in here. I hope that's a very short little story behind this work. So, okay, let me go ahead and start. See if this works. How to advance my, if I know how to advance my slides. Okay, here we go. So I just want to motivate this research a little bit. I don't really think this is necessary for the audience in here because we all work on this neutral carbon emission projects. And you are all expert in this area, of course, but just for a sort of completeness. I would like to start with this plot of this atmospheric pressure, atmospheric CO2 concentration over the years since the Industrial Revolution. So clearly we can see that there is a sharp increase. If I can just, excuse me, laser pointer, that's better maybe. So clearly we can see that there is a sharp increase over, especially since the last 60 years ago. Okay, so there have been up and downs in the US in terms of support for climate change related research, but no matter how the politicians look at this, there is a clear evidence that we are having a climate change problem or we are having a CO2 emission problem. So that's no question. Okay, so currently we are emitting about 35 to 40 billion tons of CO2 per year globally. Okay, however, to achieve the goal of less than 2-degree warming, as UNEP predicts, we will have to achieve net zero CO2 emissions by middle of the century, which is around this year in here, 2050, basically. Now, if you compare now, where we are now, and this net zero emission, so this is the gap, or this is the difference we have to reduce by in the next 30 years. So how do we do this? So I²CNER has laid out 6 major avenues to reduce CO2 emissions, as shown in this plot in here in this figure. And this number, by the way, this 36.9 billion tons CO2 emissions is the yearly emission in 2017. So it basically means that we have to get rid of all of them by 2050. And it's predicted that 20% of this reduction has to be done through CO2 sequestration or some negative emission technologies. So there are a number of options to do CO2 sequestration or CCS in general, but the one we have been interested in is the geological sequestration, which is the last one here. And in this technology, CO2 is collected from large single sources, such as fossil fuel power plants, and they are compressed, they are transported, and directly injected into acidic aquifers. And this approach has many advantages, such as that they are relatively cheap to do, they have low cost, and they have very large potential capacity and very high technological readiness. And most importantly, and we have a lot of knowledge already learned from CO2-based oil recovery, so which is basically very similar process as CO2 sequestration. So however, at the same time, there are a lot of challenges. So one of them is the range of scales. So if we really want to do CO2 sequestration in aquifers, we are essentially looking at a problem from tens of kilometers for the field scale, all the way down to a few microns, even a few nanometers. So the range is enormous. The range of scales is enormous. And the other challenge is that prior to injection, we will have to simulate and predict the migration of CO2 underground in order for site selection and also post injection, we will have to accurately monitor the CO2 migration to make sure that they do not come back up. Right? So it is well known that those large scale simulations must account for this pore-scale physics in order to be accurate. So currently, many of those pore-scale physics is still largely missing, and the links across scales are sort of missing. So our research in the past 5 to 7 years has been primarily focused on the pore-scale phenomena in order to bridge that knowledge gap. Okay, so just a little bit more background sort of on the pore-scale physics. So pore-scale flow really controls the large-scale flow. If you consider multiphase flow at pore-scale, there are 2 important forces. One is viscous force, and the other one is capillary force. So the competition of those 2 forces leads to sort of those instabilities at the interface, which cause the onset of the so-called fingering. Okay, so if you look at those two videos in here, so they show how CO2, which is the green part in here, and invades the water, which is the blue part in here, at different flow rates. So on the top, where the flow rate is high, you have, so where the flow rate is low, you have capillary fingering. And in that case, the fingering, the green phase can go in all directions, whereas on the bottom one, the flow is dominated by viscous fingering, where the flow predominantly goes from left to right. And as we'll show a little bit later, so the inertial effects can also be critical in certain conditions. So the goal of this research is to first, we want to develop this methodology to study two-phase flow in porous media at the pore scale. And also we want to quantify this physics at the reservoir conditions. So before I go to my experiments, I would like to sort of briefly introduce these two important tools that we have been using to study pore scale physics. One of them is the microfluidics. So for those of you who are not familiar with microfluidics, microfluidics is, in short, is the manipulation of fluids in microchannels. They are used extensively in energy, thermal sciences, and many other fields. So if you look at this scale in here, microfluidics is generally in between of 1 micrometer to about 1 millimeter. Here are a few examples showing that how microfluidics could be used in thermal transport and energy research. And this video in here shows the generation of liquid drops or emulsions. And the other one, this video in here shows the multiphase flow of steam and oil for oil recovery in porous media. And this picture shows the flow boiling in the transfer study. So microfluidics really has a lot of unique advantages because of the small size and because we have a very good control of the geometry and the channel properties. So by taking advantage of the microfluidics techniques, we can build a surrogate porous media using photolithography, for example, or silicon etching, or simply soft lithography. So here's a photo of the micromodel, one of the micromodels that we have been using. And I will come back to this point a little later, but just give you some sort of a quick introduction of this micromodel we have been using here. Okay, and the other tool that we have been using is called particle image velocimetry, or PIV. And again, PIV is basically an optical method to quantify flow fields. Okay, so if you have a flow in here, we can see this flow with particles, or we call flow tracers, and we limited this tracers with the laser. And then we use the camera to take images of those tracers. So by doing some image processing, and we can track the motion of the tracers, and that way you can get the velocity fields in the whole field. Okay, so this method is non-intrusive, could be done in 2D or 3D, and it will provide very high resolution data, both temporally and spatially, and also has very high accuracy. So the basic idea behind this is to do a pattern match, basically, between two images. So for example, we have one image pairing here that with the time delay of delta t. So we divide this image into small windows. We call this interrogation windows. And we do cross correlation between this window in the first image and this window in the second image. So by using this formula here, this cross correlation formula here, we could get a sort of a correlation map for this window, and this peak in here will tell us how much displacement we have between those two windows. And from that, we can get the velocity fields for that location. Okay, so basically by doing that for every single window we have in this image, we could get the full flow field for that measurement domain. Okay, so hopefully that's enough sort of preparation before I talk about my own experiments. So for this talk, we'll try to show maybe two different experiments. One is a millimeter scale measurement focusing on the characterization of the miscible displacement process and interface dynamics. And the other one is the pore scale measurements, which focuses on the individual pore scale events. So this one is simply give us a higher magnification, a higher resolution, but a smaller measurement domain. Well, on the left, we got a much larger measurement domain, but with a slightly lower resolution. Okay, so let's take a look at this millimeter scale measurement in here. So for this millimeter scale measurement, we fabricate this micro model in silicon and glass, as shown in this plotting here. And so the pore section is about 7 by 5 millimeters, and the depth is only 30 micrometers to ensure that we have 2D flow. And to do this experiments, we pre-saturate this micro model with water from the red port in here, and then we inject CO2 or supercritical CO2 to displace water from left to right. So this is what this micro model looks like. And this green region here is our measurement domain or the field of view. Okay. And the CO2 phase is tagged with the fluorescent dye in here. So it will show a color. And as the displacement process progress, and we use a high-speed camera to record this whole process. And for this experiment, we are particularly interested in how this displacement process varies under various capillary numbers and how the interface dynamics change under various capillary numbers. Okay. And here's the schematic of the flow apertures that we use to drive the flow. And remember that we are dealing with supercritical CO2, which is actually is not, to be strict, it's not supercritical. We call this sort of compressed liquid CO2. The condition is 21 degrees C, 80 bars. So the pressure is above the critical pressure, but the temperature is slightly lower than the critical temperature. So, but anyway, so that means that the pressure of the flow is very, very high. So we use this pressure cell in here to contain our micro model so that the external pressure of this micro model and the inside of this micro model is balanced. So this micro model does not break even at 80 bars. And again, we pre-saturate this micro model with water from the right with this water pump in here, and then we displace this. We inject CO2 into the micro model from the left port, which displaces this water phase from left to right. Okay, so here are two sample videos at two different capillary numbers. So the one on the left shows mostly the capillary fingering, and the one on the right shows mostly the viscous fingering. Okay, so here the solid is in black, and the CO2 are showing in green, and the water is showing in blue. Okay, so again, CO2 drives water from left to right, and clearly you can see that the difference between those two flows. So when the capillary number is low, we have the CO2 displacement is quite compact, and it can go in all directions. So it can go in horizontal direction, but also can go in transverse direction. And sometimes it goes even against the bulk flow direction, going backwards, basically. However, on the right-hand side, when the capillary flow is high, the flow is more sort of directional and is dominated by the bulk flow direction. Okay, so now if we do this for a few more different capillary numbers, here I'm showing you 9 different cases for 9 different capillary numbers spanning about 3 orders of magnitude. As the capillary number increases from this lowest case to the highest case in here, and we have a transition from capillary fingering to a crossover regime and viscous and eventually to a viscous flow fingering regime. Okay, and it clear. I mean, so naturally you can see that this capillary fingering regime will give us slightly higher displacement efficiency than this crossover, and the viscous flow regime will give us the highest displacement efficiency. So if we plot the displacement efficiency, meaning that how much water is being displaced by CO2, and we can see that the CO2 saturation, which is the vertical axis in here, at first decreases as a function of capillary number, and then increases with increasing capillary number. So there is a minimum of CO2 saturation occurring at the crossover flow regime. And this because at this capillary number, this capillary effect is sort of suppressed compared to the low capillary number case, so that this transverse propagation of the fingering is suppressed. But the viscous effect is still not strong enough to open up new pores. So that's sort of the cause both suppressions of the transverse propagation and also the flow direction propagation, and which give us a sort of a minimum flow, minimum displacement efficiency in here. Okay, so that's one of the findings that we have from this measurement. And the other thing, another thing that's very interesting to look at is the interfacial length, which can be important for capillary pressure measurement, for example, and also for the mass and the momentum transport quantification. So as shown in this video in here, the interfaces are created as the infiltration process continues, which are indicated by those red segments in here. So in this video, we have essentially two types of interfaces. One is the capillary associated interface, as indicated by those red segments in here, red lines in here. And the other one is the film associated interface. So which are, for example, in here, right? Between the non-wetting phase and the solid, there's a very thin film of wetting phase, and those interfaces are film associated interfaces. So for this work, we only consider those capillary associated interfaces for now, okay? So one very interesting result I would like to show you here is that the interfacial length as a function of CO2 saturation at various capillary numbers. So this is the interfacial length, and this is the saturation, and this is the corresponding different capillary cases, okay? So we can see that if you draw a vertical line in this plot, so for the same saturation of CO2, and we can see that the interfacial length actually increases as the capillary number increases. And this suggests that we have more or longer interfaces are being created at high capillary number, even for the same saturation. So, and this is actually confirmed by the visualization as shown in this plot in here. So on the top, we have a low capillary number case. And in this case, you can see that the interface only occurs at the front of the finger, okay? But for the high capillary number cases, because there's such a strong inertia effect, there's such strong shears, and only part of this pore is invaded, okay? So that caused a lot more interfaces being created within the pore space, okay? So that will give us, for the similar saturation, that will give us much longer, much more interfacial length. So now if we plot the PDFs of the interfacial length, so basically if we have a series of frames and we can do the processing for each frame, and we will get a large interfacial segments, and if we plot the PDFs and interfacial segments, and we do notice that this case in here is the low capillary number case, and that's the PDFs. And this bottom case in here is the high capillary number case. And we do notice that, so the longer interfaces are more probable at high capillary number. So this confirms our sort of conjecture that when the capillary number is high, there's more longer interfaces created. Okay, and also we did some LBM simulation with our collaborators, and this simulation was done by Dr. Diogo Boster's group, and actually this for the same conditions and for the same setup, we see very similar geometry in here. Again, you see that for this high capillary number case, we have partial invasion of this pore space, and that creates a lot more interface at those high capillary number cases. Okay. So the high-speed imaging also allowed us to quantify the dynamics of interfaces. So all those previous results, they are sort of static or quasi-static results. But those high-speed imaging can also do so you could compare the current frame with the next frame. So that will give us the difference, how much basically the interface moved between the current frame and next frame. That will give us sort of a quantification of the movements of the interfaces. So in this experiment, we have observed sort of three possible movements of the interfaces. That's advancement, which is shown which is indicated by those red arrows in here. So this red curve shows the interface location at the current frame, and this green curve shows the interface location at the next frame. So this is clearly advancement of the interface. And those red arrows, those blue arrows in here shows the retractions. So when you have advancement in here, you may have some retractions at the neighboring interfaces. And the third motion that is possible is that we have a motion of blobs. So basically, at the front of this blob, the interface is moving forward, and at the back of the blob, the interface is retracting backwards. Okay, so now again, if we compare this current frame with the next frame, we could get the interface speed. And again, we plot the PDFs of the interface speed at various capillary numbers, and we'll get those plots in here. Okay, we have a lot of plots in here, but I would like to show, sort of focus on maybe the bottom left one in here. Okay, so by the way, so those are horizontal velocity components. This is the vertical horizontal component. This is the vertical velocity components. This is the velocity magnitude, and this is the velocity direction for the interface advancement. Okay, so if I may ask you to focus on this bottom left panel in here, and you can see that for the PDFs that at the 3 lowest capillary number cases, the PDFs are almost identical. Okay, and this suggests that for this range of capillary number, the interface motion or interface jump is sort of independent of the bulk flow rate. And instead, they're controlled by some sort of intrinsic timescale, which could be the geometry or the surface tension or the other fluid properties. Okay. However, when the capillary number was high, or when the flow speed is much higher, this interface speed is overrun by this bulk flow, and that's creating much larger flow speed, as indicated by this blue lines, blue curves in here. Okay. So, okay, just to summarize what I have so far. So we have seen that as we increase the capillary number from very low to a very high value, we have a transition from capillary fingering to crossover to viscous fingering. And we have more interfaces produced at a high capillary number due to the strong shear and inertia effects. And also that this pore-scale dynamics, they are sort of independent of the bulk flow at low capillary numbers. Okay. So that's pretty much all the sort of the millimeter scale experiment. And now let's sort of switch gear a little bit to look at a bit closer at those pore-scale events. So now we are basically losing the big picture, but we have a closer view of the pore-scale events with much higher magnification. Okay. So for this experiment, we use the same micro model, but with much higher magnification. And also, instead of dying in the CO2 phase, which is this phase in here, we are adding tracer particles into the water phase. Okay, and the tracer particles is 1 micrometer polystyrene particles. And this is our field of view in here. You can see that the field of view is much smaller now. And again, the CO2 drives the water from left to right. And for this experiment, we are specifically interested in the quantitative velocity fields, and also the interfacial velocity or his jumps, the velocity, the instantaneous velocity during his jumps. And particularly how far does those pore-scale event propagate, or the zone of influence of those pore-scale events. And lastly, I will show some data to show the effect of avoidability. Okay. So before I get into all the details, let me play this 2 videos in here to give you some idea of this displacement process. So in here, the green part now is the water phase now, okay? And the dark region is the CO2 phase, and the gray regions are solid, okay? So you can see that the CO2 is invading in the porous media by sort of the capillary fingering. We have lots of things going on. We have a sort of fingering, we have jumps, we have sort of the sudden burst events. And if I process those particle images, and I can get, see if this works. Okay, so I can get this velocity fields at each instantaneous moments. So basically this coloring here shows the velocity magnitude. And let's see if I can do this again. Maybe not. Okay, so the color here shows the velocity field, and the arrows shows the flow directions. So again, during this process, there's a lot of sort of high velocity events. There's a lot of sort of sudden blinks of the velocity fields. Okay. So we really have learned, so this experiment, by the way, was done about 6 years ago. So we have learned a lot really from this experiment. For example, we have successfully captured this burst event. So I believe that was the first time that anybody has done that. And so during this burst event, we measured that this velocity at the interface caused a Reynolds number as high as 40. Okay. And their effects also could propagate through the porous media as far as 35 pore diameter. So if you look at the dimension here, we have about 2 millimeters of zone of influence. So that's almost traditionally considered as Darcy scale. Okay, so basically what we have learned is that those pore-scale events can affect all the way to the Darcy scale. So you have to consider those inertial effects or the pore-scale effect, even though you have a much larger domain. Okay. This is pretty much what we have learned from this experiment, but I'm not going to into more details about those measurements. Indeed, I would like to show you some that more recent measurements, which I think is more interesting. So the thing is that previously we have focused on this characterization of individual events. So basically we can only capture one event, but even though we captured one, but we actually missed more. So there's a lot more happening, but due to the low frame rate we had before, we have missed a lot. So since the burst events they are successive, they happen in a very high frequency, and many of them occur in a cascading manner. Okay, so even though we have answered those questions, here many more questions still remain to be answered. So for example, how do those local instantaneous successive hinge jumps control Darcy scale flow? And what frequency do they happen? And what is the collective effect on the flow? And what does the high velocity mean for energy balance, for example? And if we have a sort of very high flow speed, does that mean that we have very strong kinetic energy effect? Okay. And how does wettability of the solid matrix modify such micro scale dynamics? Okay. So with that, we have designed a different micromodel, which is sort of a circular micromodel, and with the pore section made up of polydispersed cylinders, as shown here. So the porosity is about 44%, and again, the depth of the micromodel is about 30 micron deep. Okay, so I would like to note that our micromodel is a circular one, so we have a sort of radial displacement now. Before we have a linear displacement, but now we have a radial displacement. So we pre-saturate this micromodel with water again from the side of the micromodel, from the edges. And then we do the injection through the center. So the center, the CO2 will be displacing water in the radial directions, and which is open to the surroundings. Okay. And again, we use micro PIV to characterize this flow, and all the experiments were performed at 80 bar, 21 degrees C. And in this talk, I will show you two cases here, both at the flow rate of 5 microliter per minute. And one is the hydrophilic case, where we have contact angle of about 9 degrees. And the second case is a sort of a neutral or slightly hydrophobic case, where we have contact angle of about 98 degrees. So here's some technical details or PIV, and we see the water part. We see the water phase again with tracer particles, and our field of view is about 4 by 4 millimeter, and the image speed is 800 hertz. Okay. So before going into other details, again, here's a video of the displacement process for the hydrophilic case. So the white region here with the particles is the water phase. Sorry that I'm changing the color scheme sort of very often. But now the water is the white region, okay? And the dark region is the CO2, and the circles are the solid phase, okay? So this video on the right is the instantaneous velocity field which is corresponding to this visualization here, okay? So you can see that the color indicates the velocity magnitude, and arrows shows the flow directions, okay? And as you can see that this flow is dominated by successive, which is evident by those blinks in the velocity fields. and pore-scale burst events that's caused hinge jumps. Okay, and due to those occurrence of the burst events, we have a lot of high momentum pathways are caused by those local hinge jumps. Okay, and also those hinge jumps, we measure that they could introduce velocities almost 2 orders magnitude larger than those bulk velocities. Okay, and one of our goal here is to identify all the burst events in this drainage process and try to evaluate their collective behavior on the flow. Okay, so here we identify this burst event based on this instantaneous volumetric flow rate. So just as an example, so what I'm showing here is the velocity vector plot for steady state single phase flow. Okay, so we have injection in the center. So according to continuity, the volumetric flow rate, they crossing any circles that enclosing the center port should be a constant, right? Because any flow that passing through this circle should eventually pass through this circle as well, right? So because water is largely sort of incompressible. Okay, so if we have that as shown in this plot on the right, we should have a constant flow as you move the circles outwards. Okay. However, in here, when the circle is very, very small, when this circle is very close to the injection port, we have very large errors or uncertainties of the velocity measurement. So that causes some sort of errors in here. But once we pass that about a quarter radius, and the velocity measurement is pretty consistent with expectation. So that also confirms our sort of measurement of the PIV. Okay, so now we can apply the same method for the instantaneous flow field as example. So when there is no active burst events, so if you calculate the flow rate crossing this circle in here, you will see very little flow rate. However, when there is one active burst event happening here, the flow rate would be sort of relatively high. Okay, so if you do that for all the moments that we have in here, and we are essentially getting a velocity, a volumetric flow rate as a function of time. Okay, and that's showing this plot here. Okay, as you can see here, there are a lot of spikes corresponding to the occurrence of the burst events, and also there are a lot of quiescent period. So this dashed line, by the way, shows the bulk flow rate, which is 5 micrometer per minute. And we then could analyze this sort of the signal to get the duration of each event. And based off that duration, we could also analyze the size of this event. And that is shown in here, okay? So this is the histogram of the burst event durations. So basically, we have identified all the burst events and we characterize how long each burst event could last during that for the lifetime, basically. Okay, so we can see that this duration could be as short as 4 milliseconds, but it could be as long as 60 milliseconds. This is primarily due to the events occurring in a cascading manner. Okay, so our calculation also shows that more than 75% of the accumulated flow rate can be attributed to those burst events. Okay, and the other thing that we can do is we can estimate the spatial extent of this burst events. So this blue bar in here shows the PDFs of the pore size, and this red bar in here shows the PDFs of the burst event size. Okay, so once we get the velocity fields, we can basically do a thresholding of the velocity fields based off the bulk flow rate, bulk velocities, and this region actually gives us the area of the burst events. And using this equation, we can get equivalent radius of this burst event. And those are those two plots in here. So you can see that this PDF is almost shifted by 2 orders of magnitude, again, than the pore size. So which means that we have much, much larger burst events than the pore size. Okay. And now that if we sort of change the variability of the pore structures, so to modify them to be hydrophobic. So we can see that, again, this white region is water, and this dark region is CO2, and the circles are solids. So you can see that the innovation process is much more mild now. They are sort of very compact, they are very axisymmetric, and velocity are generally very small. So you don't see as much as blinking from the velocity fields, for example. Okay, and by the way, the scale in here is actually different scale from the previous one. But still, you also see a little bit of sort of bursting event, not really bursting event, some sort of a burst event, a high-speed event occurring as at the edges of the CO2 region. Okay. So if we look into those pore-scale events and compare why that happens, okay. So for the drainage case, that's sort of well understood. Basically, those burst events, they are due to the sudden release of surface free energy stored on the interface. Okay. However, for the imbibition case or the hydrophobic case, which I just showed in the last slide, we have a cooperative pore filling events. So basically, what happens is that so there are two fingers coming from different directions, and each of them has one interface. And once they merge into the new pore, and the interface actually merge to create a much shorter interface. So those energy stored in the interface in this frame actually is much higher than the free energy stored in this interface in here. So that excess energy is converted to the kinetic energy into the velocity. Okay, so I believe that's a sort of a new mechanism we have identified for the pore filling events. So and to compare them sort of more quantitatively, here I'm plotting the PDFs of the instantaneous velocity for both cases. And the green here is the drainage case, the red here is the imbibition, and the blue here is the sort of a single phase flow case as a baseline comparison. And you can see that the highest velocity we can see during the drainage process is about 50 millimeter per second. And that is again almost 50 times larger than the bulk velocity. However, the PDFs for the sort of imbibition case or the hydrophobic case resembles the single phase flow very well in a large part. Okay, so that suggests that this capillarity or capillary effect and burst events are significantly suppressed during that process. Okay, but still we see a little bit of high speed events in here, and we believe that is because the merging of the interfaces, which causes slight release of the surface energy, which turns into kinetic energy. Okay, so last but not least, we did perform an energy balance, so to understand energy breakdown convergence during those displacement processes. So what happens is that during the drainage process, the flow is driven by external pump. So the external work is converted to surface energy and kinetic energy. However, for the imbibition case, actually the pressure drop is a negative value, so it's a negative number. So the surface energy is sort of spontaneously converts to external work and kinetic energy. So from this plot on the left, you can see that the external work, about 90% of the external work is converted to surface energy, and about less than 1% of that energy is converted to kinetic energy. And during this imbibition case, about 20%, which is 23 in here, the slope, 20% of that surface energy is used to do work to the surroundings. And again, very little of that energy is used to do kinetic energy. Okay, so for both cases in here, the kinetic energy are negligibly small. Okay, and again, to summarize the second part of this talk, so we have captured those burst events, which shows that the flow is dominated by successive pore-scale events called Hins jumps, and that results a velocity of 2 orders of magnitude larger than the bulk velocity. And this burst events duration ranges from about 4 milliseconds to 60 milliseconds. And those burst events are almost 2 orders of magnitude larger than the pore size. So when we have very high contact angle, the capillarity is significantly suppressed, leading to a more compact and axisymmetric displacement. Then this energy analysis suggests that kinetic energy, even though that we have very high flow speed, but due to the very high surface to volume ratio, we have very small kinetic energy for both cases. So before I close, I just want to give a couple of very quick slides on the current project that happening in my lab. So we welcome any new ideas for collaborations, hopefully in the future. So in the first project, we designed and fabricated a pressure sensor, which can be used to measure very small pressure changes in micromodels, such as capillary pressure, for example. So the sensor is based off this very thin PDMS membrane. So we have very small pressure change in here, the membrane will deflect, and then we can use the particle tracking to detect or to measure the deflection. And by doing a calibration, you could get a sort of correlation between the pressure and the deflection amount. And we can use that sort of cross correlation. We can use that correlation between the pressure and the deflection to back out the pressure change during some real experiments. So we have successfully used this sensor to measure single phase flow and multi-phase flow pressures. And it's actually very promising sensor to do sort of capillary pressure measurements, which are underway in our lab right now. Okay, and by the way, this is how we do the particle tracking to figure out the deflection. So this is based off the particle shape. As you move the particles away from the objective, the shapes is changed, and you can from the shape you can determine the distance between the membrane and the objective. Okay, so the other project we are working on is sort of mineral dissolution, which is sponsored by PRF. So this is motivated by CO2 sequestration and also acid stimulation of wellbore. So in this project, so we aim to study the interactions between pore-scale flow, which is pore-scale flow in here, and the dissolution process. So basically, when you have reactive fluids flowing in your porous media, especially when you have sort of carbonated porous media, you may possibly have some generation of bubbles, gas bubbles. So that bubbles not only change the flow patterns, but also change the surface area for reaction. So both the flow and the reaction will be affected by the reaction dynamics, by the sort of the generation of these bubbles in here. So still this is underway projects. So we hope we can do a little bit more measurements and show some interesting results later this year at a conference probably. Okay, so with that, I would like to thank all my students in here who have done a lot of work for this to make this possible, and also our sponsors, GSO2, and especially I²CNER and PRF and NSF. And so I'm also listing this related papers in here. Those cover about 6 papers we have published over the past maybe 5 years. And you're welcome to read them more for more details, or you're welcome to email me if you have any questions after this seminar. And I guess that's the last slides. With that, yeah. Thank you very much for your attention, and I would like to take any questions if you may have. Thank you.
Thank you, Yaofa. So how do we handle questions, Petros?
You take over, Ken. You read, you administer everything.
Okay. There's a hand up. Please go ahead.
Hello. Can you hear me?
Yes.
Okay. My name is Kohei Ito. I am a mechanical engineer, and my main interest is electrochemical systems such as fuel cell and water electrolyzer. So I every day challenge to solve the issue of two-phase flow in porous media. And anyway, thank you very much for very nice talking. And my question is, so you introduce many experiment picture, but which is two-dimensional. Okay, so when you consider three-dimensional porous media, my question: your main results hold, or what happened? That's my question.
That's a great question, actually. That's a very, very good question. So I think there are still, so first of all, so there are two parts of this this question, I guess. So first of all, the reason that why we do this in 2D is primarily those measurement techniques we're using is more suitable for 2D measurements. And this data was primarily used to sort of verify, to validate some pore-scale models. For example, the one that developed by Dr. Al-Valoki or the one that developed by Diego Boster. Okay, so in that sense, and 2D, this 2D sort of flow is sufficient to do that sort of a purpose.
Mm-hmm.
And the other part of this question is how do you sort of extend or extrapolate this 2D measurement to 3D measurements?
Yeah.
Actually, there's no, as far as I know, there's no good way to do that. There's still debates on how those 2D measurements is representative of real world 3D porous media. So I guess if you really want to do sort of learn 3D phenomena, you will have to design the experiments in 3D porous media and do some 3D measurements. And that's actually possible. You could do 3D PIV, for example. That's possible too. But it's very hard to link, or so how do we sort of translate the 2D data to 3D measurements? That's I think that's still open question right now.
Okay,
yeah.
Okay. And may I have additional one small question?
Yes, please go ahead.
Okay, thank you. And as I said, I am fuel cell and water electrolyzer engineer. And when we treat some porous media, we start with characterize pore distribution, porosity or tutuosity, and so on. Okay, so but I wonder today's your experiment simulate or imitate some representative real rock or just model experiment? That's my second question.
So I guess if I get this correctly, so you were trying to ask, do our geometry or micro models represent the real rock porous media, right?
Yeah,
real
yeah,
geology, right?
That's my point.
Yeah. So yeah. So as I showed in the slides, we have two different micro models. So the first one is the heterogeneous one, and that is actually the pattern that we got is also is a 2D pattern, but it's sort of from the micro CT scan of a real sandstone. So the geometry is slightly modified to make the flow measurement easier, but that's sort of a representative of a thin slice of a sandstone. Okay, so that's the first micro model. And the second micro model we have used is sort of this polydispersed cylinders. And those are just randomly generated cylinders using some algorithm that we have developed in-house. I believe that the second one is more sort of for a fundamental study rather than to be representative of the real geology.
Okay.
Yeah.
Thank you. That's
Thank
it.
you.
Thank you very much.
Thank you. Professor Suji.
Hi. Can you hear my voice?
Yes.
Yes.
Thank you very much for your nice presentations. Yeah, your movie is very impressive for me. Anyway, so I have especially I'm interested in the energy calculation part. Yeah, it was new for me. So anyway, my question is a bit different part. Can you tell me the temperature and the pressure conditions? I think the 80 bar, the pressure, right?
Yeah, pressure is 80 bar, temperature is 21 degrees C. So the critical point of CO2 is about 70 bar and 30 degrees C.
Yeah, so it's a liquid phase. The CO2 is liquid. The current the temperature
it is liquid. It's compressed liquid. Yes.
So is it difficult to increase the temperature a bit more?
It's actually not. We have actually done that. Actually, my the former student of Dr. Christensen, Professor Kazmi Fair, he did his experiments in a homogeneous micromodel.
Yeah.
And a temperature of I think about 40 degrees C. And so basically, what you can do is you can just use an incubator or use a heater to heat up your flow, right?
Yeah.
That's easier to do. But what we have noticed was that I think we are close enough to the critical point. So the physics does not change much. And the properties does not change that much. So we just decided to be easier with our life. So we just decided to use the room temperature. Yeah.
So actually this research, I'm interested in the CO2 storage, right?
Yes.
So how can I say that? Close to the phase boundary is very important, I think. So phase boundary means the liquid phase or supercritical phase or gas, because of course we would like to use the shallow reservoir because it's a lower cost, right?
Yes.
But we hope to do the liquid or supercritical CO2. We would like to store that.
Yes.
But so I would like to know this kind of the fluid characteristic as a function of the temperature or pressure, as a function of the phase of the CO2. Is it possible? My question is, can you change the temperature or pressure in your experiment? So I think it's for me, it's very interesting.
Yes, I think we should be able to control the temperature and pressure very precisely. So like if we really wanted to do that, like you said, actually I think Farzan also did some measurements in the CO2 properties near the critical point. So that's actually very sensitive to the temperature and pressure change. Okay, so I think if you really want to do that, it's actually possible. So because with our setup, currently at Notre Dame, we could do very precise temperature change. We could do very precise pressure change. So that's not a problem. I think maybe that's interesting to do for. I don't know if Dr. Christensen has has a plan for that. So you could basically repeat the same experiments at different temperatures, right? Maybe 20, 25, 30, 35, 40, right?
Yeah.
So I think that's doable. That's very doable. Yeah.
Yeah. So you are doing many experiments, right? So
yes.
If we know the temperature dependence of such characteristics,
yes,
it's really interesting. So it's my feeling. So if possible, anyway, thank you very much.
I think that'll be easier for you to do numerically, or maybe Faye could do that, right? Just tweak the parameter a little bit. Yeah. Yeah,
let's discuss later.
Yeah, sure, of course. Yeah.
Thank you.
Yep.
Professor Jiang, Fei Jiang.
Hello, I'm Fei Jiang from Yamaguchi University.
Hello.
Thank you very much for your nice talk, and nice to hear from you again. And I have several questions for your presentation. And
yes,
I think the Hennis jump, which means the burst, is a very important phenomena at the pore-scale. As you mentioned, that this phenomena will affect the Dissolution flow. So if we consider the upscaling to the field scale, how do we incorporate such a Hennis jump effect into the Dissolution flow? Can you give some comments about?
I'm not an expert of upscaling, so I don't know if I can answer this question very well. But one thing that we have tried was we had this lattice Boltzmann simulation with Professor Yaofa, or Yu Chen, you know you, right?
Yes.
And so he did a much larger domain for his simulation, and in that domain he sort of varied the viscosity so that for the same capillary number you have different sort of Reynolds number. Okay, so, and he noticed that for a change of 6 times of a factor of 6 for the viscosity change, or so basically you increase your Reynolds number from 0.01 to 0.06, and the flow patterns are very different. So you basically have more invaded pores if you have a stronger interfacial effect, or if you have a stronger inertial effect. So that's one thing that we have observed. That is actually this paper in here, this paper 5. I don't know if you have seen that paper before. And the other thing is for the upscaling, I really don't know. I don't know how to do the upscaling for the pore-scale events. Yeah, I guess we will have to do more research, or maybe involve more experts in that part.
Okay.
Yeah.
Okay, thank you. And I have a second question is about that. Most of your experiment is carried out in 2D. I think this is the limitation for the PIV measurement.
Yes.
So are your findings can your findings be directly extended to 3D real geometry? I mean the real rock geometry.
I think there are some studies recently to compare the statistics between 2D measurements and 3D measurements. If I remember this correctly, I think the conclusion was that so 2D statistics and 3D statistics are actually very different. So really? Because we are actually getting rid of one component of velocity in the normal paper direction, right? So that is actually quite different. But I guess still we can learn the physics, right? That's the whole purpose of this measurement. Even though we cannot provide sort of practical correlations, for example, but that shows the 2D measurement shows much better in terms of physics how this process happens, right? And I think so the knowledge that we learn from those 2D measurements is still useful for those 3D studies.
Yes.
Yep.
Okay, thank you. Thank you very much.
Yep.
Are there any other questions?
Okay. Can I ask a question?
Yeah, sure.
My question is a bit naive, but I'll ask it anyway. Why do you worry about the kinetic energy? Is it something that is important as far as the storage is concerned?
So, yeah, that's a very good question, actually. So, so first of all, this kinetic energy. So I guess the motivation of doing that analysis was more for curiosity. Because we see a lot of this, we see very high speed, we see very high sort of velocities. But I mean, you would intuitively sort of think those high speed events would correspond to large kinetic energy, right? Because it squares to, it scales with v squared, right? And then we did this calculation and noticed that those kinetic energy are actually negligible. And then we went to the literature and we found that actually a lot of people has been trying to do that in the past few years, trying to understand the role of kinetic energy, because they have to do this breakdown. So where did the energy go, basically, right? Mm-hmm. How much is the energy is dissipated, for example, right? Mm-hmm. And in those analyses, because they didn't have velocity measurements, so they didn't know how to account for kinetic energy, right? Some of the work maybe assume that we have a 2% in this kinetic energy, and some of the work they just don't consider it at all, right? So I guess that's this. So this measurement basically confirmed that the assumption that people have been making before is not too bad, right? It's not such a bad assumption.
Okay, good.
Yep.
Mm. And so I'm assuming all this work scales with the economics of the project. Is that, can I make this correlation?
I'm sorry, can you ask that question again?
The work, the expenditures that you have there, right? Yes. The energy expenditures must be scaling also with the economic of the project, right? That those will be setting the pressures and how expensive the project will be. In other words, to push all this CO2 inside the pores.
Yeah, I guess that's one aspect to this. But I guess more of those this energy analysis is it gives you a fundamental understanding of this process, basically, right? It's so the energy, because energy has to be conserved. So where did that go? Like how much you're giving the system this much work, and is that work being used to drive the flow? Is that work simply dissipated, right? So I guess that's the other aspect of this whole analysis. Yeah.
Thank you very much. I mean,
Thank
impressive experiments. Thank you.
Professor Fujikawa.
Yeah, thank you very much for your nice talk. I'm a CO2 capture researcher, so I have some question about the concentration effect of the other gas. Usually, you know, you are using the maybe very pure CO2 gas. Why? Can you hear me? Can you hear me?
I didn't quite get it. It was cut off for a moment. I can hear you now. Yeah.
Can you hear me?
Yes, I can hear you now. Yes.
All right, good. How can I say? In your experiment, you know, you are using the pure CO2 stream for the fluidics, but you know, realistically, it contains some other gases, oxygen and nitrogen case. So actually, I'm doing some CO2 capture from the air. In that case, also captured gas stream contains rather high contents of the oxygen and nitrogen case. So in that case, if such kind of other gas species or molecule may affect something in the flow dynamics of the CO2. So do you have any comment, or will you have some plan to do such kind of mixture type of the experiment?
I don't really have an insight for that. I think that's a very good question. That's very interesting problem to study for the future. But currently we haven't considered any impurity of the CO2 at all. So yeah, I think that's probably I can look into that sort of more carefully in future experiments. I think that's a very interesting direction to go. Yeah.
Actually, we had a discussion with Professor Tsuji, and then it is rather difficult to understand the three mixture of the nitrogen, oxygen, and CO2 at a higher pressure condition. Under high pressure condition, we don't know what is the behavior of such kind of three mixture system, but realistically, such kind of mixture will be used for such kind of CCS.
I see.
That is why I think this is very interesting for me. And if we that is why I think maybe Tsuji Sensei may have comment.
Yeah, I guess there's just, I mean, that's another thing we have to consider to make our experiments more realistic, probably, right? So because we have so many simplifications. Yeah, I think that's something very interesting to look at.
Please do it.
Yeah, I'll try. I'll be happy to talk more about this. Yeah.
Right. Okay. Thank you very much.
Yeah. Thank you.
Do we have any other questions or comments?
If I follow up with what Professor Fujikawa said, I'm assuming a mixture will modify the surface energy, right? And that will affect the surface energy terms.
I think first of all, it will change the surface tension, that's for sure, right? And the other thing is that if you have different mixtures in there, with different components in there, they have different phase behaviors. So I recently looked at one study about those nanopores. Actually, in nanopores, because the capillary pressure is more important than those micropores, in that case, you may have sort of evaporation happening, for example, or some phase change behaviors due to those high change of capillary effect. I don't know if that's a problem for this microscale flow, because the pressure change is not that significant. But still, I think that could be something that affects and maybe Dr. Tsuji can add on this. I'm just guessing, I guess. Yeah.
Yeah, the behavior is become very complex. Actually, we investigate the behavior using the MD, molecular dynamics simulations. But of course, if the how can I say, the purity of CO2 is low, we needed to inject to the deeper reservoir, the higher pressure condition. Yeah, so as Professor Fujikawa said, we are very interested in the low purity CO2 system. Because currently the Professor Fujikawa's project is the DAC, direct air capture system. So the purity of CO2 is low, but other component is very natural one, nitrogen and oxygen. So we may be able to inject the such low purity CO2 in the geological system, but the behavior is we don't know the such a low purity CO2 behavior in the geological formation. So we would like to know that.
Yeah, I see. Yeah, thank you for the insight.
Are there any other questions or comments? If not, thank you, Yaofa, for a very interesting talk.
Thank you very much for
everyone
hosting.
for attending. Absolutely. Petros, you want to say anything to close?
Yeah, thank you. Thank you very much. Yes, indeed, an interesting, very interesting talk, and well presented. And also, I think this area is very important. It is becoming increasingly important these days. As you know, the part of the hydrogen economy, right, involves what we call blue hydrogen. And at least right now in the United States, there is a mobilization amongst the states about CO2 storage, right? Hydrogen generation by reforming methane and then storing the CO2. In fact, a month ago, the state of Indiana, right, the neighboring state, right, passed legislation, and they said that they will explore sequestration of CO2 in this basin that we have in the Midwest. As you know, it is one of the most safe storage sites in the United States. So this is really, really very important research. And both in I²CNER, we are pursuing it. And along with Professor Fujikawa, I think we can accomplish this goal, carbon neutrality by the year 2050. So Lee, we are looking forward to engage you in discussions with our institute and in Japan in general.
That'd be great. Thank you very much. Yep.
Thank you very much. Thank you. Takeshi, would you like to add anything?
Yeah. So yeah, I agree with you. The currently the CO2 storage project is many CO2 storage projects are ongoing. So this kind of I think many audience feel this is a bit fundamental work, but the currently we recognize the importance of such the pore-scale behavior. So and it's very easy to understand the CO2 behavior. So honestly speaking, the public people worry about the CO2, how the CO2 migrate in the subsurface, but this study, this movie, it demonstrate the clearly the such CO2 migration process. So it's a very important for the public understanding too. So sorry for it's my poor comment. Anyway,
absolutely.
Thank you very much for
very important comments, Takeshi. Very important. Thank you, Professor Fujikawa. Would you like to add anything?
No.
All right.
No.
Okay. All right.
Maybe you want to sleep.
All right. Thank you.
Thank you.
Thank you all. Thank you very much. So let's thank the speaker once again for this wonderful webinar that we had on this day in I²CNER. Thank you again.
Thank you.
Thank you.
Bye-bye.
Bye.